Yes, Sandeep, you can start. Yeah.
Okay, so enormous pleasure to welcome Sanjoy Dasgupta online for this talk, for making time for us this late in the evening this time. Thank you so much. We are very keen to have you visit us physically and spend time with us whenever the opportunity allows us, hopefully not too far from now. But thank you for making this time. A little bit about Sanjoy. His PhD is from Berkeley in the year 2000. Then he worked for a couple of years in AT&T Research Lab before joining University of California, San Diego. As most of you know, his area of research is in algorithmic statistics with a focus on unsupervised and supervised learning. He has a very famous textbook along with Christos Papadimitriou and Umesh Vazirani on algorithms. Today's talk is on convergence of nearest neighbor classification. Sanjoy.
Okay, yeah, thank you very much. Very happy to be talking here. And yeah, hopefully we'll make it there in person, sooner rather than later. Yeah, so I'm gonna, talk about something that is very dear to me, and that's nearest neighbor methods. So nearest neighbor classification, this is one of the oldest, most popular types of classification. It's really very simple. So you have a training set of a bunch of data points, x1 through xn. Each point's got a label. If it's binary classification, there are only two labels, let's say 0 and 1. And you don't have to do anything with the data, you just store it. When you get a query point and you want to predict the label at that point, you just look for its nearest neighbors. So let's say this is the query point. You look for its nearest neighbors amongst the training points. You look at their labels and you take the majority vote of those labels. Okay, super simple. And so the question is, how can we formally characterize the performance of this method? So the method itself is so simple that one would imagine that the analysis is also really easy. And it is, but it has taken a really, really long time, many, many decades. And there are still a whole bunch of questions that need to be answered. So at a high level, just some notes about this classifier. First of all, it's a non-parametric estimator. And what that means is that the more training points you get, the more complex the classifier is. So here I have a picture where there's a data set of, I don't know, about 15 points. And this is the decision boundary carved out by nearest neighbor. Okay, it's already quite complicated. And as the number of points grows, you can get very, very complex looking decision boundaries. Okay, so everything on this side is labeled plus, everything on this side is labeled minus, and this is the boundary between them. So the sort of questions that one asks about this kind of estimator is, first of all, how expressive is it? What kinds of boundaries can you actually get with this classifier? Can you get any boundary, or are there some boundaries you can't get? Second, as you get more and more training points, does the boundary converge to something? And finally, what's the rate of convergence? Okay, so we'll look at all of these questions. But before we get there, we need to just make things a little bit more precise and introduce a bunch of notation. Okay, so the data are going to be in some space X, and we need a distance function on that space with respect to which we'll find nearest neighbors. And most of the work on nearest neighbor has looked at the case where the data lie in a Euclidean space and the distance is L2 distance. We'll be looking at the setting where it's a metric space. Okay, so that's going to be the setting for today. But it's also of interest to look at more general spaces, at distances that aren't metrics, simply because nearest neighbor is used often with distance functions that have been handcrafted for a particular application. And so they might not be metrics. And so it's kind of interesting to also think about what happens in those scenarios.
Sanjoy, a quick question for you. First of all, is it okay if we interrupt in between? We have a small group, or would you prefer that we put the questions in the chat?
Either way, yeah, you can just ask questions or put them in the chat. Either way, I'll.
Okay, sorry about that. So very quick question for you. You know, the majority rule that you're using and you're putting all these properties for it, if you were to use a different rule, say weighted distance and all that, some kind of sum of weighted distance, would much of what you say, would it generalize? Should we keep that the way we think about this, or?
Yes, so right, so one could definitely use a weighted different, some sort of weighted distances. You know, and something like that actually becomes necessary when there are multiple labels. You know, if you look at, if you're doing 3 nearest neighbors and there are 3 possible labels, you know, then, you know, and they all end up being different, then you have to break ties somehow. And so you would use distance. Right, so I think that a lot of it would generalize, but there's probably some property that one needs for the weighting rule, you know, just some, you know, some simple thing that it would have to satisfy to make everything work out properly. And I'm not sure what that is. So I think it would be, yeah, that would be interesting just to clear up in a situation with multiple labels and some sort of weighting rule that one uses for tie breaking. What property does that rule need to have? I don't know of any kind of crisp formulation for that.
Thanks.
Okay, right. So there's so this is the instance space. Okay, so this is where the data lie, and now we're also going to have a distribution on that space. So we'll be following the sort of standard setup of statistical learning theory, where the assumption is that there's some underlying distribution from which all data comes, past, present, and future. And it's really this distribution that kind of ties the past and the future together, and that explains why learning is possible. So this distribution in this case is some measure mu on this space X, and all points come from this, okay? And so we actually have a metric measure space, the space X, the distance metric D, and this distribution mu. So that's how we get the X's. And now for any X, its label Y, 0 or 1, is a coin flip. And it's a coin flip with bias eta of X. So eta of X is just the probability of getting label 1 at X. Okay, so the labels are not necessarily deterministic. In some settings they are, you know, it's like if you're trying to, if you're doing, I don't know, some sort of, let's say, object recognition or something, it's probably fairly deterministic. You know, you say, okay, this is definitely a giraffe, that's definitely a zebra. But in other settings, like medical diagnosis, for a particular X, all sorts of outcomes are possible. So in general, we'll think of the labels as being stochastic, and this conditional probability function will give us the biases. Okay, so this completely specifies the data distribution, the distribution mu on X's, and then the conditional probability distribution of Y given X. Now, the thing we want is a classifier, which is a rule from X to a label 0, 1. And the error rate of a classifier, its risk, is simply the probability that it's wrong on this underlying distribution. Because of the stochasticity in the labels, there isn't necessarily a classifier that's perfect. But the best possible thing to do is the Bayes optimal classifier, which on an instance X will predict 1 if the bias of the label at X is more than 1/2, and otherwise it'll predict 0. There's nothing better one can do. And in that case, the chance of making an error on X is the min of eta of X and 1 minus eta of X. And so the overall error rate is the expected value over X of this. And so this is the best possible error achievable on this distribution. It's the Bayes risk. And what we'd ideally like is to converge to the Bayes optimal classifier, or more precisely, to converge to the Bayes risk. We would like a classifier whose error converges to this. Can't do any better than that. Okay, so now that all the notation is there, let's see what the questions are that we want to ask. So let H sub n be the nearest neighbor classifier based on n training points. So the first question is, does the nearest neighbor classifier converge to the Bayes optimal, or rather, does the error rate of the nearest neighbor classifier converge to the Bayes optimal error rate without any assumptions at all? Okay, so one doesn't want to make assumptions, for example, on things being smooth and so on. And it turns out that this is true. This was shown in the 1970s for finite dimensional Euclidean spaces. So one thing that we've done more recently is to extend this to more metric spaces. Okay, and I'll be talking about that. The next thing is rates of convergence. Okay, so it converges, but how fast does it converge? And unfortunately, in non-parametric estimation, there are no distribution-free rates of convergence. It's not possible to say it's going to converge at a rate of 1 over n squared or anything like that. The convergence rate really depends on the distribution, okay? And in particular, smoothness matters. So for instance, here are two pictures. Here is a data space X and a conditional probability function, eta of X. And so for this kind of data, you'd want to predict 1 over here and 0 over here. And this is relatively simple. This is a situation where there's lots of bumps, and you probably need a lot more data to figure out where those bumps are. Okay, so it really seems like the smoothness of this function matters. And so
Sanjoy, one question.
Yeah, please go ahead.
Yeah, so you're plotting eta x with respect to x. So as x increasing, what does it mean? Distance from the origin, or what is x?
Oh, so sorry. Yeah, so in this case, I'm just looking at a simple example where the data lie on the real line.
So x is just a distance from the origin?
Yeah, x is just the actual data point. It's just a real number.
All right, thanks.
Yeah, I just wanted to draw something in 1D, and that's what it is. Yeah. So so the typical way that this goes in the statistics literature is that they say that, well, it's not possible. We need to assume something about the distribution. So let's assume a whole bunch of smoothness conditions, and then give rates of convergence in terms of those particular smoothness parameters. And it was shown a while ago, for example, that what the best possible rates are. And one of the things that we show is that nearest neighbor attains these minimax-optimal rates. I personally do not like these rates with lots of smoothness conditions. And so, and in particular, for something like nearest neighbor, one really feels like one should be able to give rates of convergence that are not just minimax-optimal over some large smoothness class, but are actually correct for the individual distribution and maybe even for the individual query point. And so that's also something that we have, that's also something that we've done. And so these are the various sorts of things that I'll be talking about. Okay, so here's a question on the chat. Can we use convolution to make things smooth and then take the limit to deal with non-smooth data? Ah, okay, that's interesting. So, so I guess the answer would be the following. Okay, so typically when one is doing convolution, so for example, you're convolving with a certain type of Gaussian noise, you have to pick the width of the noise. For example, the variance of the Gaussian. In the case of nearest neighbor, we want to fit arbitrary decision functions, okay? So in particular, the label can jump from 0 to 1 in arbitrarily small intervals. So if we were to do something like this convolution, it would not be possible to do to pick a Gaussian of fixed width and use that same width as n approaches infinity. One would have to choose a schedule in which the width of the noise was shrinking appropriately, and I'm not sure what that would be. Okay. So these are the things I'll talk about. Getting consistency, that's actually just converging to Bayes optimality, but doing it without any assumptions. Then rates of convergence under smoothness conditions, and then rates of convergence that are really accurate for the individual distribution. Okay. So let's start with consistency. So let's say we have this training set, x1 through xn, and their labels. How do we answer a query? So here are three options. We could just look at its very nearest neighbor, that's one nearest neighbor, or we could look at its k nearest neighbors and give the majority vote, or we could do k nearest neighbors, but let k grow as the training set grows. It turns out that the first two options are not consistent. Okay, so for example, one nearest neighbor is not consistent. And here's a simple example of why. Let's say the data lie on the real line or whatever in any space, but the labels are basically coin flips with bias eta 0. Like let's say coin flips with bias a quarter. So whatever, so for any x, the label is just a coin flip with bias with a probability a quarter of coming up 1. So what should you do? You should just predict 0 everywhere. That's the best possible thing to do. And what's the error rate? It's eta 0. It's a quarter. That's the error rate. But now let's see what happens with one nearest neighbor. With one nearest neighbor, it doesn't matter how many training points you get. You have a query point and you have its nearest neighbor. And their labels are both coin flips with bias a quarter. So the chance of being wrong is that those two coins come up different. So it's a quarter times 3/4 plus 3/4 times a quarter. And so it's more than a quarter. So one nearest neighbor is just not consistent. And similarly, k nearest neighbor for a fixed k also has a risk that is the minimum possible, eta 0 in this example, plus some fixed function of k that doesn't go to 0. So if you want consistency, you have to do k nearest neighbor and you have to let k go to infinity. So though that's the sort of nearest neighbor classifier that we'll be using. There's no getting around that. Okay, so I'll talk about one of the first results about consistency of nearest neighbors, the one by Cover and Hart.
Sorry, Sanjoy, what was the definition of consistency? I just got a bit lost on that.
Right, yeah. The definition of consistency is that as the number of training points grows, the nearest neighbor method converges to Bayes optimality.
Oh yeah,
so,
I got it. Okay.
Right, yeah. So that's and so that's the best you could hope for, but it's actually taken a while for the community to figure out exactly how to do that for nearest neighbor. So so the first results about consistency one actually required a continuity assumption on this eta function, on these on the probability that y equals 1 at x. Okay, so it required it to be continuous. And Fix and Hodges showed in 1951 that under this continuity condition, you get consistency in Euclidean space with L2 distance. And Cover and Hart showed in the 60s in a series of 3 papers that under this continuity condition, you get consistency in any metric space. Okay, and let me tell you what the argument is. It's a nice argument. It's also very simple. So this is how it goes. Okay, so let x be a query point. You want its label, and let's say you have n training points, and let's just order them by increasing distance from x. Okay, now the training points, all data comes from this underlying distribution u. So if we look at any ball in space, the number of points in that ball, the number of training points in the ball will be approximately n times the probability mass of that ball. And what that means is that if we look at the ball containing the k nearest neighbors, it's a ball that is centered at x and whose probability mass is about k over n. Okay. Now, we're going to ask that k over n goes to 0. So we want k to go to infinity and k over n to go to 0. And since k over n is going to 0, it means that as the training set size grows, we're looking at a ball that's getting smaller and smaller. And so the nearest neighbors are getting closer and closer to x. Now, we also have this continuity condition. Since the nearest neighbors are getting closer and closer to x, their conditional probability values, their coin biases, are also getting closer and closer to the bias of x. And so ultimately, you're in a situation where the nearest neighbors have essentially the same bias as x, and you just use the law of large numbers. We're using a larger and larger value of k. You are just, and the nearest neighbors have essentially the same bias. So the fraction of ones amongst the nearest neighbors will be approximately the bias of x. And so simply taking the majority label will do the right thing. So that was the argument by Cover and Hart. And you can see how it used continuity. The nearest neighbors are getting closer and closer to x, and therefore their bias is getting closer and closer to the bias of x.
Sorry, Sanjay, if I could just ask, only where does this argument fail for fixed k? Why does this not work for fixed k?
So it doesn't work for fixed k because for fixed k, there is a fixed probability that, so if you toss those k coins, there's a fixed probability, some function of k, that the majority vote will not be correct.
Okay.
So you need k to go to infinity, basically.
Okay.
Hi, I also have a question. So do we have something about how this k should go to infinity? So maybe this k goes to infinity, but extremely slowly. That it's basically a constant for any practical purposes, like maybe something like inverse Ackermann function, something weird.
Right. So for this particular argument, k can go to infinity very slowly. Later on, we will, it'll turn out that we will want k to be, let's say omega of log n. But this argument will be okay with very slowly growing k. Okay, so that was 1960s. And then in the 1970s, there was this huge breakthrough by Stone, who was able to show consistency in Euclidean space without any assumptions at all on eta. So without the continuity assumption. Okay, and so I'll briefly indicate how that went. So the starting point was Leusen's theorem that, look, so we're not going to assume that eta is continuous, but it's measurable, which means that it's close to a continuous function in the sense that for any epsilon, there is some continuous function that agrees with eta everywhere, except on an epsilon fraction of the distribution. Okay, so in other words, eta is continuous everywhere except on some bad regions of the space. And we can make that bad part of the space as small as we like, any constant. Okay, so there's this bad stuff over here, but other than that, eta is nice and continuous. So what is the effect of this bad part? What it means is that if you have a training point in this bad region, its eta value is anything, and so its labels are troublesome. So hopefully those training points will not be our nearest neighbors. If we can avoid those training points as our nearest neighbors, we're fine. But can we? And that's the question. Is it possible that even though there's just a few of these points, like this point, could it be everything's nearest neighbor? Is that conceivable? And so that's the question that they had to resolve. And it turned out that it can't. If you look at any finite data set, then any one point can be the nearest neighbor of at most a constant number of other points. And because of that, these small regions of space, this epsilon-sized region of space, cannot infect the whole space. Its influence is still O of epsilon. Okay, so let me tell you how that goes. Okay, so this was the key geometric fact. They say, pick any finite number of points in, say, p-dimensional space, and pick any one point, x. How many of the other points can possibly have x as their nearest neighbor? And it turns out that it's at most 5 to the p of the other points, where the p is the dimension. Okay, and so let me explain the argument. So the way you show this is you say, well, let's look at cones of a fixed angle, like 30 degrees. Let's look at 30-degree cones subtended at that one point. Okay, so we have these cones subtended at one point, and let's cover the whole space by these cones. Now, since the cones have a fixed angle in this 30 degrees, or maybe it has to be 15, I don't remember. Since the cones have a fixed angle, the number of cones you need is basically 2 to the d. In this case, it's 5 to the p. Okay, so that's the number of cones you need to cover the whole space. Now, within any cone, only one of the points in the cone can have this as its nearest neighbor. If you look at this cone, for example, this point in the cone can have the red point as its nearest neighbor, but this can't because it's actually closer to this point because the cone is so narrow. Okay, and so this is why any one point can only be the nearest neighbor of a constant number of other points. Okay, and this made it possible to show universal consistency, to show consistency in Euclidean spaces. So what we were interested in doing now is moving to metric spaces. And now these
Sanjoy, a quick question for you. So now query point can be a bad point in all of this, right? You know, for example, eta x is something on rationals and something else on irrationals. If the query point is a funny point, but I guess you're averaging away, you're saying the measure of that is 0?
That's right, yeah. So the bad set we can make as small as we like. But and so the chance that the query point falls in that is, you know, it's if the bad set is of size epsilon, right, the chance that the query point falls in there is only epsilon, and epsilon going to go to 0. What we're worried about is that, you know, a training point in there can actually affect lots and lots of query points.
Mm-hmm.
Right. So, okay, so recently we, well, not that recently, about 7 years ago, we were looking at universal consistency, trying to do it for metric spaces. And we showed it for some limited class of metric spaces, actually fairly large class, but it needed a different kind of argument. Okay, so let me show roughly how that goes. So again, there's a query, and now we get a bunch of training points, and let's say we order them by increasing distance from the query. The previous argument, which was that of Cover and Hart, said that under continuity assumptions, since the nearest neighbors are getting closer and closer to the query, their eta values are also getting closer and closer. So their biases are getting closer and closer to the bias of X. And so we can use the law of large numbers. Okay. So one thing that we observed is that we actually don't need the bias of all of the nearest neighbors individually to approach the bias of X. We just need the average of their biases to approach the bias of X. Okay, so if there are 100 nearest neighbors, we don't need that individually each of their biases approaches that of X, but just the average of those 100 biases approaches that of X. So that's a much milder condition. Now, these nearest neighbors line some ball around X, some ball of radius R. And if we choose R carefully, we can actually think of these nearest neighbors as random draws from the underlying distribution restricted to this ball. Okay, so, and therefore the average bias of these nearest neighbors is actually close to the average eta value in this ball. Okay, so we have this ball around X. The nearest neighbors are essentially random draws from this ball. And so the average bias of those nearest neighbors is close to the average eta value, the average bias in the ball. So the integral over the ball of the biases divided by the probability mass of the ball. Now, as we grow n, this ball gets smaller and smaller. We get closer and closer to X. And so this is the average bias. It's the limit as R goes down to 0 of this average bias. And if this limit turns out to be eta of X, then we can just use the law of large numbers just as before. And looking at this, this is in, so in normal Euclidean space, this is just the fundamental theorem of calculus. This is just the derivative of the integral. And more generally, this is Lebesgue's differentiation theorem. And so in any metric space for which this holds, we automatically get universal consistency. And so that was the result. Consider any metric measure space for which this Lebesgue differentiation property holds. Okay. If so, then the risk of the nearest neighbor classifier goes to the Bayes optimal risk. So what are the kind of spaces for which this holds? Well, finite dimensional norm spaces, metric measure spaces that have the doubling property, certain types of directionally limited spaces. Okay, so so this was a different style of argument from before, just based on replacing this, instead of considering the nearest neighbors individually and looking at the individual biases, looking at the average bias of the neighbors. Okay, so I've talked a little bit about consistency, universal consistency. Now let me talk about rates of convergence, okay? And as I said, the most common thing in statistics is to look at rates of convergence under smoothness conditions. And so what are these smoothness conditions? It turns out that there's a standard bunch of them. So the first smoothness condition, the one that's usually used, is to say that this eta is Holder continuous. And it's simply that if you look at any x and x prime, the difference between the eta values has to be bounded by some power, some alpha power of the actual distance between them. Okay, so just kind of like a Lipschitz condition, but with this power as well. And that's just saying that eta is smooth. The other condition that usually gets applied in this case is to say, well, eta has to be smooth, but at the same time, we cannot have eta being close to a half everywhere. That would also be bad. So we need it to be the case that the boundary isn't too highly populated, isn't too densely populated. And so we say, let's look at all points whose bias is a half plus or minus t, okay, where t is something small. We want to say that the probability mass of such points is at most some function like this. Okay, so there just isn't, it cannot be the case that everything's right at the boundary. So this gives two parameters, alpha and beta. And it was shown by Sivakov and Audibert that if these two conditions hold, then the best possible rate of convergence is this. Okay, that you cannot get this is the best possible rate of convergence in terms of the dimension p, the whole parameter boundary condition beta. And one of the things that we showed is that k nearest neighbor actually achieves this minimax optimal rate. Okay, so one thing I should say is that I really dislike these types of results, because these kind of minimax optimal results, you see what's happening is that there's a very large family of situations that are being considered over here. Okay, so we are saying, look at all situations that satisfy this smoothness condition and this boundary condition. So it's a huge number of cases over here. In these cases, you have some that are easy, and then you have some that are hard. And what we do in looking, when we talk about minimax optimal, you're looking at this, like the very hardest thing over here. And you say, oh, for that guy, that's so hard. That guy, you're going to get this rate of convergence. That's the best possible. But now, if your estimator gets that same rate of convergence for the easy examples, you still say it's optimal, which is crazy. You know, maybe you're forced to, maybe you kind of have to do that for parametric methods. But for non-parametric methods, you really should be able to do better. And so that's something that we really wanted to do. For something like nearest neighbor, you should be able to get rates that are really tight for the specific distribution, not for some huge smoothness class of distributions. And so I'll say a little bit about that. So, so we have two types of results. So the first result I'll talk about is by talking about smooth distributions, but saying that if distributions are smooth, we can actually get a rate that's tight for the individual distribution. And in order to do that, we introduce a new smoothness condition for nearest neighbor. So the Holder smoothness condition is a very generic condition, and it isn't really ideal for nearest neighbor in the following way. So the Holder condition is basically trying to bound how fast this function eta changes. And it bounds it. It says, okay, let's look at eta at x, and let's look at eta at x prime. How much does it change? And we bound it in terms of this distance. For nearest neighbor, the actual raw distance doesn't matter. What really is important is the probability mass of this interval. And so instead of bounding the difference between eta x and eta x prime in terms of this distance, what we said is, how about instead bounding it in terms of the probability mass of this interval? And so we introduced this other condition, this alternative to the Holder condition, where we say that for any point x, the difference between its probability mass, the difference between its bias and the average bias of a ball centered at x is at most the probability mass of the ball raised to some power alpha. And it turns out that this, if you have Holder continuity, then you also have this kind of continuity. So it just follows from Holder continuity. But then what's the benefit of introducing this other smoothness notion? So now it turns out that if your eta function satisfies the smoothness condition, then you can give rates of convergence that actually have a matching lower bound. You can show that the best possible error rate is simply the probability mass of points whose bias is a half plus or minus 1 over square root k. And that for an appropriate setting of k, that's also the error rate obtained by k nearest neighbor. Okay.
Sanjay, my apologies. Many of us were having network trouble, so we were going back in and out. I just want to check with Ramprasad and Piyush, is this recording on the YouTube going to be continuous, or will we have a discontinuous function there? Can we go back and look at all this, whatever we missed?
So outside of PIFR, it was okay.
Oh, I see. Wonderful, wonderful. That's very good. So whatever we missed, we can go back and catch up on it. Sorry about that, Sanjay. Please carry on.
I didn't, I didn't, like from my end, it didn't seem like there was any discontinuity of any kind.
No, we missed 3 or 4 slides, I think.
Yes.
Okay.
Can we go back and look at all this?
Yes, I was also having the same issues, but I think the YouTube thing is working fine.
Okay, so yeah, let me just give like a very quick, like 10-second summary then of the last 3 or 4 slides.
That'd be great.
And that is that we introduced a new smoothness condition. And under that smoothness condition on the conditional probability function, you can actually give tight rates of convergence that are tight for the specific distribution, okay? And in fact, the rate is something very simple. The probability of error is basically the probability mass of points whose bias is a half plus or minus 1 over square root k. That's the probability of error. And there's a upper and lower bounds of that form. Okay, so it differs from the sort of minimax-optimal analysis in the sense that it's actually distribution. It's tied at a distribution-specific level. Okay, so under the hood of these kinds of results are actually an analysis that gives a rate of convergence for specific distributions. But I won't go into that. I'll just talk about now some work that we've done where we're actually able to give rates of convergence that are very simple and that are specific not just to the distribution, but even to the specific query. Okay. So the starting point for this is this question of, well, with k nearest neighbor, how do we choose k? What is the right choice of k? And this is actually very tricky to do, as this picture shows. Okay, so let's say in this picture, the data spaces say R. Okay, so the data lies on the real line. And these are the eta values. So for example, in these points, the eta value is maybe something like 0.45. And over here, it's 0.55. And so over here, we would want to predict 0. And over here, we would want to predict 1. Now, looking at this, because the eta values are so close to a half, we would need a rather large k. Otherwise, because we're averaging over k nearest neighbors, we're going to need a large k because otherwise we might end up on the wrong side of the boundary. So just looking at this part of the input space, we would say, oh, k should actually be pretty big. But if we use a big k, then we run into trouble over here. Now over here, if we use a big k, we end up averaging in points. So we're averaging in these points as well. And we could end up with the wrong label in that sense. Okay, so picking k is hard. And just a picture like this really makes it seem that maybe k should be chosen in an adaptive way. Where the right thing to do over here is to pick a small value of k in this part of the space and a much larger value of k over here. Okay, and how would one do that? Is there a simple way to do that? So we defined an adaptive nearest neighbor classifier. Here's how it works. So you have your training set, that's as always. And now you're given a query point and you want to find its label. So this is what you do. You take your query point and you grow a ball around it. And you look at the training points in the ball. You look at their labels. If the labels have a significant majority of ones, you predict 1. If they have a significant majority of zeros, you predict 0. If they don't have a significant majority, you keep growing the ball. And you keep growing this ball until you finally get a significant majority. And if you never get a significant majority, you just say, I don't know. Okay. And so this is the adaptive way of choosing k. You just grow the number of neighbors until you finally get a significant majority. Okay. And if it never happens, you say, sorry, I don't know. Okay. What does a significant majority mean? It means basically a half plus 1 over square root k, or a half minus 1 over square root k. And there's also a log term in there. Okay. So this is nice because it avoids having to choose k. And it turns out that under this, you can give really clean rates of convergence. And so let me go over that. So what we did is to introduce a non-parametric notion of margin. Now, margin is one of the standard ways of analyzing linear separators. If the linear separator has got a little margin around it, then life becomes much easier in many ways. Now, when one is dealing with non-parametric estimation, the margin is most naturally actually a function on the entire space. So we introduce a notion of margin where, so basically the margin is a function from the space to 0, 1. Each point in the space gets this margin. And if m of x is close to 1, that means x is really easy. It's a point that's easy to classify. If m of x is close to 0, it means the point is hard. So I'll go through the notion of margin. It's over here. But let me first say what the result is. So the result is that, so this notion of margin actually completely controls the rate of convergence in a query-specific way. So if the query is x, the prediction at x will be correct when the size of the training set exceeds 1 over the margin of x. Okay, so if the margin at x is close to 1, you just need a tiny training set. If the margin at x is close to 0, then you need a much larger training set. Okay, so it's a very clean rate of convergence. And it really points out what are the points that are hard to predict at and what are the points that are easy to predict at. Okay, so I'll go ahead and just define the margin. For any given point, so let's say we have a point x, let's look at a ball around x. Okay, and as usual, when we're talking about balls with nearest neighbor, what matters is not the radius of the ball, but the probability mass of the ball. That's, everything is probability masses, okay? Okay, so now we'll say that x is, let's say x has got a plus label. Let's say x has got a label of 1 without loss of generality. We'll say that it is p gamma salient if every ball around it whose probability mass is less than p has the same average label. Okay, so this is the average label in ball. Okay, so we're looking at balls of probability mass p. So every ball of probability mass, every ball centered at x of probability mass less than p has got the right average label. And moreover, if you look at the actual, the ball of probability mass exactly p, or the first ball whose probability mass exceeds p, that ball has got a bias of a half plus gamma. Okay, so it's got a significant bias. And if that's the case, we say that point x is p gamma salient. And what that means is that it is gamma salient, its bias is a half plus gamma at the probability scale of p. At the scale of probability mass p, its bias is really apparent at a sort of a half plus gamma level. Now, the margin at any point is the supremum over all p gamma squared for which x is p gamma salient. And so let me just explain why that's the case. So if the point is p gamma salient, what that means is that the probability is that the average label is that the average eta value in this ball is a half plus gamma. So it's significant. And what that means is that if you have 1 over gamma squared points in this ball, you'll get the right label. Okay, but the ball has probability mass p. So in order to get 1 over gamma squared points in the ball, the number of points you need overall is 1 over p gamma squared. So if the number of data points is p gamma squared, you will get 1 over gamma squared points in this ball, and then you'll get the right label. And so we take the supremum over all of these p gamma squareds for which x is p gamma salient. And that's how we end up getting this, this notion of margin and this rate of convergence. Okay, so so in terms of open problems, there is just a huge number of them, and as machine learning tries to do more and more things.
Sorry to interrupt.
Yeah, please go ahead.
Yeah, probably due to network issue, I missed it. So you mentioned about some bad sets, right? Of epsilon, we can make the sets in the beginning when you should introduce the notion of the bad sets, right? So if we take a point in the bad set, so what can you tell about the nearest neighbor about that point in the bad set?
Right. Yeah. Right. So the bad sets, So the bad sets were points whose bias was essentially arbitrary. It's like there's a small number of points whose label could have been set by an adversary. A small number of training points. Imagine that some epsilon fraction of points where you can choose epsilon had their labels set by an adversary. What effect would that have, right? Now, that would be really bad if every query point had a nearest neighbor being one of those guys, one of those bad guys, right? But the geometric fact that that we saw was that actually any point can be the nearest neighbor of at most a constant number of other points. So even if there's a small number of points whose label have been set by some bad guy, the effect of that is limited.
Okay, thank you.
Okay. Yeah. So in terms of open problems, one open problem is we have this notion of margin, and I think that there's just a lot to. This is the first non-parametric notion of margin that I know of, and I think that there's a lot of interesting things to do around there, including experiments. Another thing that I'm very interested in is looking at consistency in more general topological spaces. So as I was saying, metric spaces are, of course, a nice and large family of distances to look at, but very often nearest neighbor is used with custom distance functions, or even things like KL divergence. What happens in those cases? What can be said about consistency and so on? The next question is an extension to countably infinite label spaces. I don't think, I don't think that there are a huge number of technical challenges there, but that would be interesting to work out, since most of the work has really just focused on the binary case, and so I don't think this has been fleshed out properly. And finally, nearest neighbor, once one has rates of convergence for it, one can use it for all sorts of things, domain adaptation, active learning, and so on. So there's actually a huge number of open problems around nearest neighbor. There are also all these new learning scenarios that are now coming into prominence, things like one-shot learning, okay? Or learning to learn, so meta learning, all this sort of stuff. And, the first system to analyze for all of these is typically nearest neighbor, because it is so clean and transparent, and it's sort of a nice guide to what can be achieved non-parametrically. Okay, so I'd like to thank my co-authors. So with Kamalika Chaudhary, we did some of the work on a universal consistency, and then with Akshay Balsubramani, Yoav Freund, and Shai Moran, we worked on the non-parametric notion of margin.
So I had a question. So in terms of this different metrics, so where does, for example, the cover heart argument fail for any other metric? It seems that it sort of goes through for any. So just redefine the notion of a ball. So it's only using continuity and the scaling of balls probably. So.
Right. Right, I guess. So there's a couple of other parts of the covariant Hart argument that I kind of swept under the rug. So for instance, so for example, one of the things that is argued over there is that as the number of training points grows, so the k nearest neighbors get closer and closer to the query point. And so even that was a little bit, so the other thing Cover and Hart did was to define this notion of the support of the distribution, where, actually, let me just write it down. So the support of the distribution is basically the set of points for which the probability mass of a ball of radius r is greater than 0 for all r. Mm-hmm. And so what they showed is that
but this will again be the same for all equivalent norms, for example. So all LP to give you the same.
So this, right? So this requires. So what one needs to show is that is that almost every point lies in the support. Is that, and so this. Yeah, so this comes from, I guess, just from separability, maybe. But yeah, I think it would be interesting to see what if anything.
That's something like if the metric has the same topology, if it induces the same topology, then it works or something like that, because.
Yeah, I mean, if it can, if right. Yeah, a lot of the so certainly in our work, when we were like looking at this Lebesgue differentiation condition and so on, we ran into a lot of, so we ended up using a lot of results from the analysis of metric spaces. And the generalization of that to more general distances seemed like a big jump. It involved some more complicated geometric measure theory, but at the same time it looks like a really fun area.
And the second question I had was about this the margin notion. So is it sort of some kind of a robustness already built into it? So you think you're already talking about adversary. So if there is actually an adversary who is corrupting a certain fraction of points, is the margin notion already somehow strong enough to take care of something like that it will work, it can analyze the k nearest neighbor even under the presence of a certain adversary who is actually allowed to corrupt a certain number of labels? Not
Right.
just
Yeah. So I guess there are two different things, but I don't know if either of them relates to margin. And so one is just that, I mean, just inherently with nearest neighbor, if you corrupt just a few points, it doesn't affect a large part of the query distribution, which is nice. Just because of that earlier result. And the second is that, yeah, just choosing a large value of k automatically does give some sort of robustness. Yeah.
Can I ask a question? So this can be thought of as learning whether eta is greater or equal to or greater than half, right? This process of. So what if you actually were interested in estimating eta exactly, or learning eta, a regression, sort of a regression question? Do these methods help?
Right. Yeah. So there's so yeah. So absolutely, one would just again take the k nearest neighbors, and now just look at, so instead of taking the majority vote of the labels, just take the average label.
I see.
Just the average of the, yeah.
I see.
And then the arguments will go through as before.
I see. Thank you.
Any further questions? Okay, in that case, let's thank Sanjoy for a very lucid talk, very clear talk, and also a very elegant set of new ideas. So I really enjoyed it, and the parts which I missed, I look forward to going through them soon.